Okay, so there are two approaches to determine measurement uncertainty. The first is to repeat an identical measurement enough times to enable statistical analysis. We'll talk about that one in great detail in this lecture. The second approach is to determine the measurement uncertainty of the instrument, typically using manufacturer specifications, and I will talk about that one in a subsequent lecture. So let's circle back and talk about this first one, the statistical approach. So there's two really important aspects of this. First is the word identical. We are taking identical measurements because we are trying to eliminate a systematic error. Now, we accept that when you take measurements, there must be random error. That can't be avoided, but systematic error should be eliminated at all costs for this method really to work. And so when I say identical measurements, what I mean is you're literally measuring the same thing over and over and over again. You are using the same measurement instrument. You are making sure that the system that you're measuring itself doesn't change in any meaningful way from one measurement to the next. Typically the same person takes the measurement, and that measurement is being taken in a very limited time frame, so that the environment surrounding the experiment doesn't somehow change and throw off the measurement. So it's really important to reduce and eliminate systematic error in these repeat identical measurements. If you don't, if you somehow allow the system to change from one measurement to the next, then this approach does not work because it assumes that there are only random errors and not systematic errors in your measurements. Now, the second item of importance is you have to take a statistically meaningful number of measurements. Now, if you start to talk with mathematicians, statisticians, they'll tell you that you can start to calculate averages and standard deviations once you've accumulated about more than 10 values is what they'll tell you. So I'm an engineer, a number more than 10, well, that's 11, right? So at least in this class, we'll be taking 11 identical repeat measurements as we use this technique. If you can take more, so much the better. 100 is better than 10. 1,000 is better than 100. 1,000,000 is better than 1,000. But as we'll see, it often becomes prohibitive to take that many measurements. So we'll take 11. That's a statistically meaningful number of identical measurements. Now, let's talk about some pros and cons of this technique. So the benefits are the following. First, you have your statistically meaningful number of measurements, your 11 measurements, and you can calculate an average and a standard deviation, and those are statistically accurate values that can be used to determine the uncertainty. If there's ever any doubt as to how you came across those values, you can actually show somebody who's a skeptic how you calculated them. And that's very important and very meaningful to have that foundation as you report these quantitative experimental values. The second benefit is that the resulting uncertainties are usually a bit smaller than the uncertainties that you would get using that other approach, using the specifications of your measurement instrument as stated by the manufacturer. And I'll talk about that in a little bit more detail in a subsequent lecture, but we won't focus on it now. The key drawback for the repeated measurement approach, as I described before, is that it's costly in terms of time and sometimes even in terms of money to take a statistically meaningful number of measurements. So what I'm talking about here, to take identical measurements, let's say, for example, you wanted to measure the mass of a ball bearing. What you would do is take your ball bearing, find an appropriate scale, zero the scale, put the ball bearing on the scale, record its mass, lift the ball bearing off the scale, zero the scale, put the ball bearing back down on the scale, take the measurement again, record the mass, and repeat that over and over again at least 11 times, a statistically meaningful number of times. Now, that's a simple example, but if your interrogation technique, if your measurement technique is very expensive, very complicated, very difficult, you can imagine it becomes really hard to take a statistically meaningful number of measurements. So you, as the engineer designing the experiment, designing the measurement technique, have to decide whether you have the resources and whether it's worth it to pour those resources into this repeated statistical analysis approach for experimental uncertainty. So that's the drawback. Now, let's talk a little bit about how this would actually work. So you now have your statistically meaningful number of measurements, your 11 measurements. Again, more measurements is better, but of course more costly. And you then take those 11 measurements and you run them through this averaging equation to determine an average value for those measurements. And I will give you an example both of the averaging equation and this following standard deviation equation in the course, so you can see how this is done. This average value that you get from your statistically meaningful number of measurements is the actual experimental value that you would report. Once you have that average value, you then have to calculate a standard deviation, which will lead you to the experimental uncertainty. Determining the standard deviation is done using this standard deviation equation here, and again, I'll have a demonstration in the course to show you how this is done.